Hi, in this video, we are going to talk about the double slit experiment. This is a very important experiment. As you know that in the end of the 19th century, beginning 20th century, there was a big crisis in physics, and lots of experiments were done at that time, which sort of pointed that the classical theories of physics were wrong. And double slit experiment is one of those experiments. And today we are going to go into the details of the double slit experiment. So let's start with the setup. So the setup is the following. You have a source plate. So let me draw this over here with a hole in it. And there is some source which could be emitting some particles. And then you have a plate that has got two slits. You have a plate that has got two holes in it. So this is, and then finally you have a detector plate, which is some farther distance from these double slits. So this is a source plate. This is the plate with two slits, so double slit plate. And this is the detector plate. Okay, and then let's say you have some particles like bullets that are emitted from here, and they are indestructible particles. So either they could go from hole number one or hole number two over here. And then the detector sort of is able to detect the particles. And what we are trying to look for is the probability that the particle arrives at a certain point on the detector. So maybe you have a holder over here that catches these particles, and then you hold it for a certain unit amount of time, and then you see how many bullets or particles arrive at this point, and then you move this, shift it over, and hold it over here, and you count, and then you plot the distribution of particles. So the other thing you could do is that you could close one of the holes and do the same experiment. And if you do this experiment with, let's say, with hole one open, then you will get some distribution which looks something like this. So you will get some distribution that is like this. So this is the probability of arrival of particles. And if you open hole two, then you may get some distribution which looks like this. Right? And that makes sense. If you are close behind the hole, then your probability of arrival at that point is higher. And then if you open those holes, then you will see that the probability distribution of the particles look somewhat like this. So you have a sort of a double hump, right? And suppose I label as P1 as the probability of the particle arriving at that point, given hole 1 was open. And similarly, we label P2 as the probability if hole 2 was open. And P12 is the probability if both holes are open. Then you see that this particular graph is the sum of the two graphs that are drawn if either hole 1 or hole 2 was open. And we can have a simple counting argument that P12 is indeed P1 plus P2. And the main reason is that the particles are indestructible, and the particle can either go from hole 1 or go from hole 2, but it cannot go from both holes. So therefore, this is the situation for particles in the double slit. Now we can change this up a little bit. So instead um, of particles, now suppose this source is a wave. So this can be either a particle or a wave. It could be a water wave or something like that. And then the situation is slightly different. So if the particle was a wave, then the wave front gets created over here. So let me draw these wave fronts. So the wave is coming out from the source hole. And then when it hits this double slit, then it separates out into two waves. The hole 1 and hole 2 become new sources. So you have these two wave fronts over here. So I'll draw this over here, right? So the wave front that with the source as hole 1 and then other wave front with the source as wave 2. So I will draw these pictures. So these are two, right? And so a single wave front gets created into two wavefronts from hole 1 and hole 2, and they interfere with each other. And therefore, um, the distribution when hole 1 and hole 2 are open is different because the two waves interfere. The one which is given by the red and the green one interfere with one another. If one of the holes is closed, then the patterns are the same as you see over here. The patterns are not different from the particles, but since waves interfere with each other, if we have both holes open, then we have an interference pattern which will look something like this. So it will be some pattern which looks like this. So it will be symmetrical pattern, that is right. So this is the interference pattern that it's created. And in this case, if we are looking at the intensity of the waves, then the intensity of uh, the wave, if hole 1 was open, so intensity if hole 1 was open, suppose I take uh, I1 as that. And similarly, so this is for particles, this is for waves, and I2 as intensity of the wave if hole 2 was open, and I12 intensity if hole 1 and 2 were open. Now, it turns out that in this case, we don't have the graph of the interference pattern is not the sum of the patterns when either hole 1 or hole 2 was open. And therefore, we have I12 is not equal to I1 plus I2. In fact, it turns out that the following holds. I12 mod square is equal to I1 plus I2 mod square. Regardless, the main difference between the classical particle and wave is that when both holes are open, the interference occurs, and the interference pattern is given by this sort of complicated pattern. And if I look at the front view of this, right, you will get essentially these fringes which are alternatingly uh, dark and light fringes. So you will get some pattern which looks like this, right? So this is the interference pattern. Now, so this is very well understood from the classical theories. But now, if you have a quantum source or a source of, let's say, electrons that are transmitted by this source on the first source plate, then something interesting happens. So, um, if you assume that electrons are particles and you transmit them, and it's possible to transmit them one at a time, you can, reduce uh, the intensity of the source to a certain extent that one could actually transmit uh, these electrons one at a time. Then you can hear, or you can see some patterns that are created on the detector plate. So when one electron gets transmitted, it makes an impression over here. So electron is observed over here. Um, and that sort of suggests that the electron is a particle. Uh, However, if you wait for some more time and let all the electrons, sort of a large number of electrons get transmitted, then you get an interference pattern just like what you observed when you saw the wave being transmitted. So this is a very surprising result, because if we assume that the electron is a particle, then it can only get transmitted from when it gets transmitted from the source, it can either enter the double slit from either slit 1 or slit 2, but not both. And so the interference pattern that should be created should be like the classical particles. However, the pattern that gets created is the interference pattern. So is the electron a wave or a particle? So that is one thing that came out of this experiment. So electron appears to have the properties of both waves and particles. The other thing that you can do is that you can sort of put a detector on one of the, you can put a detector near one of the holes and observe the electrons. So when you do that, you do observe that the detector goes off. Um, and if you put a detector on hole number 2, then you can see that the electrons gets measured by either one of the two detectors. So it means that the electron has actually passed through either one hole or the other, but not both. And then when you do that, the interference pattern is no longer observed. In fact, what you observe is this pattern. Um, so it seems that the other thing that came out of this experiment is that, measuring or observing the electron does indeed disturb the electron. So let's see the surprising facts when a source is of electrons. So one is that uh, both wave like and particle like behavior is observed. In fact, if you're, it seems that if you are not observing, then the electron behaves like a wave. But if you observe, then the electron behaves like a particle. Secondly, we have that when we have the detectors, the electron seems to be disturbed. So measuring the electron collapses the wave-like structure. And we are not able to observe the interference pattern. So one of the ways to sort of make sense of this is that let me call A1 as the probability. So instead of probabilities, now we have probability amplitudes. The probability amplitude of observing the electron if hole 1 was open. And similarly, A2 is probability amplitude if hole 2 was open. And A12 is probability amplitude if both holes are open. And so the interference patterns are created by these probability amplitudes adding and subtracting from each other. And well, the probabilities are related to the probability amplitudes by the following fact, that the probability of the particle arriving is equal to the amplitude square. The probability of the particle arriving at some point, if the hole 2 was open, is related to probability of A2 square, and P12 is equal to A1 plus A12 square, which is equal to, so A12 is equal to A1 plus A2. Just like the waves, the probability amplitudes are adding up, but the probabilities are actually the probability amplitude square. So this is A1 plus A2 mod square. And this explains the interference pattern for the electrons.